Dear viewers, welcome to the class of Fundamental Chemistry. Today I will teach you Stille reaction and Suzuki reaction. This is part 2 of our organometallic compounds. Before I will teach you Stille reaction and Suzuki, I would like to teach you about palladium. Palladium is a transition metal. It reacts with variety of molecules or ions. This variety of molecules or ion is also called ligands. So when they bind with this palladium, then it will give you transition metal complex. So in this case, palladium is bound with 2 chlorine. So you can say palladium is bound with 2 ligands. When you make reaction of this palladium dichloride with triphenylphosphine, and when you use 2 equivalent of this will give you palladium complex with 4 ligands. This palladium ligand bond, it is generally polar covalent and weakly associated with palladium center. So this means they can break or you can make this bond anytime. So the number of ligand that are bonded to palladium can change accordingly. So when your palladium compound will be stable. Okay, so here come 18 electron rule. It is similar like 8 electron rule, or you can call it octet rule. So second row element of your periodic table follow this rule. So they can accommodate 8 valence electron in their valence shell. Valence shell has 1 s orbital and 3 p orbital. And we know 1 orbital you can accommodate 2 electron, and here is 3, so you can accommodate total 8 electron. When second row elements, when they accommodate this 8 electron in their valence shell, they will become stable. So you can take it example like oxygen, nitrogen. Similarly, in 18 electron rule, transition metal having 18 electron in their outer shell or valence shell, then this transition metal becomes stable. So their valence shell has 1s, 3p and 5d orbitals. Okay, so if you calculate, you will find it total 18 electron. So in this complex, palladium tetrakis, in which palladium is bound with 4 triphenylphosphine molecules. So palladium has total 10 electron in their valence shell, and triphenylphosphine donate 2 electron. Okay, so there is total 4 triphenylphosphine means it will give you 8 electron. So 10 plus 8 become 18 electron. So in this case your palladium is stable because in its outer shell there is 18 electron, and in this state, oxidation state of palladium tetrakis, oxidation state of palladium is 0. So now palladium becomes stable, and stable are unreactive. So when you dissolve this palladium ligand complex in solvent, these ligands comes out. When one ligand come out, it will give you 16 electron palladium. When 2 ligand comes out, it will give you 14 electron reactive species. In this case, palladium again has 0 state. Okay, so this palladium 0 is reactive species. It will bind with your organohalides. Okay, and this process is called oxidative addition reaction. We will study about this step in our next reaction, which is Stille reaction and Suzuki reaction. Stille reaction. So Stille did his PhD from University of Illinois, and I am happy that I did my first postdoc from this university. And he started his independent career in University of Iowa, and then he moved to Colorado State University. There he performed Stille reaction. Based on his work, Heck, Nigeshi, and Suzuki, they received Nobel Prize in 2010. So, what is Stille coupling reaction? In Stille reaction, there is one organostanine compound. This is your organostanine compound in which organic part is attached with tin. So this is also known by organotin compound. And other part is organic electrophile, which is generally organohalide. So when your organotin compound react with organohalide compound in presence of palladium catalyst, this will give you new carbon-carbon sigma bond. Okay, so I already told you that palladium in oxidation state 0, it is active catalyst, but sometimes we use palladium 2 complex also, like palladium diacetate, palladium dichloride, diphenyl phosphine. So in this state, palladium first they need to convert into 0 state, which is active catalyst form. So next we will talk about what is R and R prime. R in RSN and R prime in R electrophile. So what is this R? So this R can be your aryl, vinyl, or any substituted vinyl. And R prime will be aryl, and vinyl. So when two aryl compound react in presence of palladium acetate, it will give you biaryl compound. When one vinyl react with aryl, it will give you styrene derivative. This is the styrene part. And when two vinyl will react in presence of palladium, they will give you conjugated diene. Regarding X part, X can be any halogen like chlorine, bromine, and iodine. And you know the reactivity of this halogen. So generally iodine is much more reactive than bromine, and bromine is much more reactive than chlorine. So these days you can see research paper OTF, which is also a good living group. What is this OTF? Before to talk about OTF, I will tell you O-mesylate. This is also known by name O-mesylate. This is nothing, just methane sulfonyl. So this is good living group. And if you remove this hydrogen with fluorine, CF3, this will become triflate, trifluoromethane sulfonyl compound. So these days you will also find nonoflate NF, in which there is 9 carbon and each carbon is attached with the fluorine atom. So regarding stereochemistry, if your both reactant has E configuration, then definitely your product will retain this E configuration. So there is retention of configuration. And how you prepare this organostanine compound? So first advantage of organostanine compound is they are not sensitive to oxygen or moisture. Like Grignard reagent, when Grignard reagent find little bit of moisture, they react with it and get destroyed. But organostanines compound are more stable than Grignard reagent. And how you make organostanine compound? First you have to make Grignard reagent by treating organohalide with magnesium. It will give you Grignard reagent, and then treat it with tributyl tin chloride. You will get your organostanine compounds. Now we will talk about reactivity. So in Grignard reagent, you have seen that if there is OH group, NH group, SH group, or acid group, your Grignard reaction doesn't happen. But in organostanine or Stille reaction, whenever there is amine hydroxy group ketone aldehyde group, carboxylic acid, amide, ester, nitro. They do not affect these reaction because Stille reaction is very selective. So whenever this stannine moiety will find good leaving group, it will attack there and you will get your required product. Here you can see there is a carbonyl compound, there is oxygen ether compound, ether type of moiety, but you are getting your product which you want. And mechanism of Stille coupling. First step is oxidative addition. So your halogen will bind with palladium ligand complex and your palladium ligand complex get inserted here and you will get your palladium ligand complex. Here the oxidation state of palladium is 0, but here the oxidation state of palladium is 2. Okay, so now your this complex will react with organostannine moiety, which is now transmetallation will happen. What is transmetallation? Transmetallation means exchange of metal. You can see your this R group is getting transferred from tin to palladium. So here R group is now on palladium. So there is transfer of organic part from one metal to other metal. So regarding reactivity or transfer of R group, vinyl part, aryl part, allyl or benzyl, they transfer very fast and alkyl transfer happens very slow. So this is the rate determining step. And reductive elimination. Finally your this part is ready. Now your palladium ligand will complex will come out. So this was the starting catalyst which was in oxidative 0 state, which is active state. So it will come out and this is your required product in which new carbon-carbon bond formations occur. So here I will tell you palladium ligand, it is very costly, but the advantage is you use it in very little amount. For example, 3 mole percent, 5 mole percent, 1 mole percent. In very less quantity, this will give you your product. Okay, so this is the advantage of organometallic compounds or palladium compounds, palladium ligand compounds. Next, I will teach you Suzuki reaction. So Suzuki did his postdoc work under Herbert C. Brown at Purdue University. Now he is currently professor in Hokudai University. So with his assistant Norio, he discovered Suzuki reaction in 1979. So the only difference, there are two differences between Stille reaction and Suzuki reaction. In Suzuki reaction, you use organoborane compounds, while in Stille reaction, you use organotin compound. So you can see your organoborane compound or organoboron compound reacting with organic halide, and now this R will bind with this R prime and it will give you final product. So this was the first difference, that in Suzuki reaction you use organoboron, and other difference is you use base. Here they are using sodium ethoxide. So in presence of this palladium and base, there occur formation of new carbon-carbon bond formation. So next we will move to regarding what is organoborane or what type of organoboranes are available in market. Okay, so your Y group, if it is alkyl, then it is known by name organoborane. If it is alkoxy like methoxy, you will call it boronic ester. If there is hydroxy group, you will call it boronic acid. Okay, so this is 2-methyl group, you will call it aryl borane. Okay, and here it is like ester group, so you will call it vinyl boronic ester. Okay, and here there is 2-hydroxy group, you will call it allyl boronic acid. And like Stille reaction, your R will be vinyl aryl allyl moiety. Regarding your organoelectrophile, your X can be iodine, bromine, or triplet OTF, and R prime will be your aryl moiety and vinyl moiety. So some of the example of Suzuki reaction I have shown here. Your organoborane ester will react with this vinyl having OTF leaving group in presence of palladium tetrakase and sodium methoxide. It will give you this styrene derivative. And here your vinyl part is reacting with another vinyl part. It is giving you conjugated diene. So what is advantage of Suzuki our Stille reaction? In Suzuki reaction you can make sp3 sp2 bond formation. So sp3, when you take alkyl and at the end you attach borane, boronic ester or boric acid, and if you do reaction with aryl halide, you will get sp3 sp2 bond formation. While in Stille reaction you have seen sp2 sp2 bond. And organoborane compound are low in cost and low toxicity compared to organotin compound. So what is disadvantages of Suzuki reaction? If there is aldehyde group and it has alpha hydrogen and also ketone having alpha hydrogen, this will go under aldol type of reaction and give you undesired products. Stereochemistry, there will remains retention of configuration E reacting with Z, you will get EZ compound. So there is retention of configuration. And how you prepare this organoborane compound? If you start with triple bond alkyne, your organoborane or organoboric acid that will contain double bond. So here phenylacetylene, this is phenylacetylene is reacting with catechol-borane, you will get this phenyl styrene. So this is styrene. And if you treat it with 9-BBN, you will get this compound. So vinyl boronic ester reacting with vinyl borane can be prepared via hydroboration of alkyne using catechol-borane or 9-BBN. So now if you start with double bond here, you will get single bond. You will get alkyl borane derivative. And your borane part will be catechol-borane and 9-BBN. If you want to make aryl boronic acid derivative or aryl boronic ester derivative, just treat aryl lithium with the boric acid and you will get your aryl boronic acid compound. And mechanism of Suzuki reaction. Suzuki reaction mechanism is same as Stille reaction. First step is palladium 0 state will undergo oxidative addition, react with organic electrophile, and it will convert into palladium 2 state. Then there will happen displacement. So here comes the role of base. Your base will displace this halide part. So sodium ethoxide will react with this, displace this halogen. You will get sodium chloride, sodium bromide, and your OET will get now attached to this palladium. Now the next step is transmetallation. So to perform transmetallation, your organoboron compound react again with base and it will give you organoborate anion. So that organoborate anion now undergo transmetallation and this arg part will get attached to this palladium. And finally, you know reductive elimination and you will get your coupling product. So these three steps are same. First, oxidative addition, transmetallation, reductive elimination. The one new step is coming, displacement and activation of organoboron compound by use of sodium ethoxide base. So this is the role of base. So whenever you perform Suzuki reaction in your lab, you generally use 2 to 2.5 equivalent of base in that reaction. Okay, so viewers, this was about Stille reaction and Suzuki reaction. In future, I will come with Sonogashira reaction, Heck reaction, and some other organometallic reaction which are currently in use in industry and research lab. Thank you.